Yeah, yes, Praveen, let's start.
Okay, sir. Yeah. So good evening, everyone. So I welcome you back to solving sessions, solving previous year gate questions asked in the area of flight and space mechanics. And my name is Praveen, and today we'll be focusing on the questions which are asked in the year 2015 in the area of flight and space mechanics. Okay. So in that year, so they asked around five 1 mark questions and four 2 mark questions, totaling around 13 marks. Okay. So this is again 14 and 15 and few other years, where the years were in which they asked questions which were not within the range as specified. You remember that, right? Okay, so let's get started with the first question of today's class. So consider the density and altitude at the base of an isothermal layer in the standard atmosphere to be rho 1 and h1 respectively. The density variation with altitude rho versus h in that layer is governed by, so we have four options. Rho by rho 1 is equal to e to the power minus g naught by rt times h minus h1. Rho by rho 1 equal to e power minus g naught by rt h1 minus h. Rho by rho 1 is equal to e power minus rt by g naught times h minus h1. And rho by rho 1 is equal to e to the power minus rt by g naught times h minus h1. Right? So let's do this pretty simple one. So what you do is just write on the if you revise the notes in the starter, I mean the JD answer. So in that he has derived the standard atmosphere model. You can just write down on the stratosphere. So the density variation of rho 2 by rho 1 is equal to e to the power minus g naught by rt times h minus h2 minus h1. Okay, if that is the case. Okay. So the stratosphere, you have to remember that your temperature remains constant. Okay? So that's why it is called as an isothermal layer. Okay. Right. So for a troposphere, in troposphere, just want to give you formula so that you know that, right? So the density variation is given by rho 2 by rho 1 is equal to T2 by T1 times G by lambda R minus 1. Okay. Where lambda is the lapse rate. Just write that down as well. Lapse rate, which is equal to minus dt by dh. This is equal to 0.0065 Kelvin per meter. Okay. So this is what is. Okay. So which means my answer has to be option A. Go back in here. Okay. Pretty simple, isn't it? Right. So let's go to the next question. Which one of the following modes of a stable aircraft has non-oscillatory response characteristics? So short period, Fugard, Dutch roll, and spiral. So underline this word, non-oscillatory response characteristic. Okay. So let's draw the plots for each and every mode. So short period looks something like this, like this. Fugard looks something like this. Dutch roll also looks similar to like a Fugard mode. Spiral is the one which looks like this. Okay. So if you refer, to the book R.C. Nelson, Flight Stability and Automatic Control, in that book they have clearly mentioned the differences. So which means the answer has to be spiral mode. Okay, spiral is the only non-oscillatory mode. The rest all others are oscillatory characteristics. Okay, so let's write that down. This is oscillatory. This is oscillatory. This is oscillatory, and this is non-oscillatory. Okay. Hope you guys don't have any doubts on this. Pretty simple, isn't it? So let's go to the next question. An aircraft can level an unaccelerated flight with a velocity of 300 meters per second. Like this. requires a power of 9 into 10 power 6 watt. If the aircraft weighs 1.5 10 power 5 Newton, the lift to drag ratio is dash. So it says level and unaccelerated flight. So I can just write that down. So in a straight and level flight, lift is equal to weight and thrust equal to drag. Right? But I also know that basically I can write the thrust as the power available by the velocity, correct? Yes, which means if I simplify this, I can write this as thrust is equal to weight by L by drag, right? Right. Which means if I simplify this, you will have the value as 9 into 10 power 6 divided by velocity is 300. So we'll get a value something. So which means again, if I substitute that over here, so that would basically be by what? L by D equal to weight by thrust. So which means if you simplify this, you will get a value, close to 5. So my answer is yes. So let's simplify this. Again, it's a pretty simple problem. No issues. Okay. So if no notes, then let me go to the next question. The percentage change in the lift-off distance for 20% increase in the aircraft weight is dash. Again, it's a simple problem. So let's do that as well. So if we recall our previous sessions, we know that the lift-off distance expression is given by 1.44 times W takeoff weight square by rho g s CL max times T minus mu times W minus L. Where you can just write that down. WTO is the takeoff weight. Additional thrust drag weight and this rho is the density. S is the platform area of the wing. Actually, it should not be CL max, but it's CL. Okay. CL. CL is the lift coefficient. And the mu is the coefficient of friction. Right? Basically, I can just say that from this expression, SL was proportional to W takeoff square, right? So which means if I simplify this, if I have a 20% increase, so that's percentage change in SL2, right? It's basically what? SL2 minus SL1 divided by SL1, which is equal to what? The new weight is 120%, which is 1.2 times, right? So that will be, substitute that. 1.2 times square is 1.44 square minus 1 square by S1. So that will closely come out to 44%. So that is the answer. Okay, so 44. Yes, any doubts in this? I hope it's pretty simple, right? Just mere application of the formulas in these problems, right? Okay. So let's go on to the next question if you don't have any doubts. A statically stable trimmed aircraft experiences a gust and the angle of attack reduces momentarily. So we have four options. What happens? As a result, the center of pressure of the aircraft shifts forward, shifts rearward, does not shift, and coincides with the neutral point. Okay, so this is not the option. So mind you, it's a typo from our side. So as a result, what happens? The center of pressure of the aircraft shifts forward, shifts rearward, does not shift, and coincides with the neutral point. Okay, which means let's try to do this. Let's say you have this CP. this is the CP basically. CP is the center of pressure where in which the net resultant lift and drag act. This lift and this drag. Okay. We have AC and CG. Let's forget that for now. Okay. Right. So which means when you basically increase the let's say it is at an angle of attack alpha. Okay. When you basically decrease the angle of attack, your CP will travel forward. Okay. So basically CP will move forward. Okay. So which means in that case, if you this is from the thin airfoil theory. Okay. Which means what I can say is when the angle of attack decreases momentarily, your CP has to move forward. Okay. It shifts forward. Right. That is the thing. I remember that, right? Because the CP is function of the angle of attack, the location of CP. So let's write that down. So the location of CP is a function of the angle of attack. Okay, this is what you have to remember. And basically, if your CP moves forward, then what will happen is that will generate a pitch down moment. Okay, because your angle of attack decreases. Correct. Again, these are pretty simple stuff. Okay, pitch down moment, and again, what that happens, what that leads to, it leads to a decrease in the altitude. Okay, so it's sequence. Okay, it's in sequence. Okay, hope you guys understand this. Any doubts, right? So let me go to the next question if you don't have any doubts. An aircraft with a wing loading of 500 Newton per meter square is gliding at L by D max of 10 and CL equal to 0.69. Considering the free stream density rho infinity is 0.9 kg per meter cube, the equilibrium glide speed is dash. So again, it's a simple problem. Let's do this. So let me write down that data, given data there. So given that, so the wing loading is given, which is 500 Newton per meter square, and L by D max is given as 10, and CL is 0.69, and the rho infinity is what? 0.9. I know from theory that let's say it is gliding means let's say this is the glide angle, let's say some theta. L by D is basically 1 by tan theta. So this is basically given as 10, right? So from here you can simply determine the theta. Okay, so determine theta. We'll do that is simply tan inverse of 1 by 10. Okay, that's what you will do. Get the value. Next. Also in a glide, let's say you have an aircraft like this, basically. Your lift is like this, your weight is like this. So which means the lift is now equal to W cos theta, correct? Yeah. So what can I say? Lift is what? It is half rho V square S times CL, right? So that is my lift, right? So that is equal to W cos theta. So therefore, I can say that what? Let's move the S to this side. So I will have W cos theta by S is equal to rho V square CL by 2, right? What is asked is V, right? V is unknown. Everything is known. Substitute the data from here. I can simply write that what? V equal to under root of 2W cos theta by rho SCL. Simplify this, you will get a value of close to 40.029 meter per second. Okay, pretty simple again. Okay, right. So again, like these, problems are more to come in the gate question. That is application of the formulas. Okay, right. So let's go to the next question. This is an assertion and reason based question. Determine the correctness or otherwise of the following assertion and reason. So we have an assertion in here and a reason. Aircraft directional static stability can be improved by moving the vertical tail rearward. Reason is because Moving the vertical tail rearward increases the momentum from the tail aerodynamic center to the aircraft center of gravity. Okay. So basically, let's light a little bit of theory in here. We have to understand. No? We write it in here itself. So by moving the vertical tail rearward, the directional static stability is improved. Basically, it's increased. Okay. Because the momentum length, which in brackets LT, increases. Okay. Let's see what this. Okay. So when you derive this expression, C and beta, you will have a VV bar. It's some function of VV bar. Okay, where the VV bar is SV times LV by SB, and the LV is basically the location of the tail from the center of gravity of the aircraft. Okay, let's take this as the CG, and this is basically my tail momentum. Okay, and if this LV is increased, basically your C and beta is increased. So C and beta is increased, then that means increase in C and beta implies increase in the stability, directional stability. Okay. So this is what you have to remember. Right? So it means my answer is A because both are correct. Okay. And R is the correct reason for it. Yes. Hope you guys don't have any doubts in this. No. So if not doubts, then let me go to the next question. So we still have two more questions to wrap up today's session. Right. Take this problem. For a level flight at cruise altitude, CD equal to 0.018 with a drag coefficient at zero lift, C not 0.015. For a 30-degree climb at the same altitude and speed, CD equal to dash. So let's do this. So we have two cases, okay, for level flight. I can write that down. Level flight. So we know that CD equal to CD naught plus KCL square. CD is given, CD naught is given, so let's determine the KCL, which is KCL square. If you substitute that, you will simply get it as it's this minus this, so we'll get it 0.003, right? Just a mere subtraction. Okay, this is for level flight. Next, for the climb, okay, climb flight. So what is given is, so in climb we know that the lift coefficient is basically what? It is cos theta, correct? Which means the CD naught doesn't change. If CL changes, your CD changes, so which means the new drag, it will be simply CD naught plus K times CL prime square, right? So substitute that, so we'll have what? It is 0.015 plus K times, CL dash square is what? CL cos theta to the whole square. So I'll have 0.015 plus K CL square cos square theta. So K CL square is can be used in here 0.03003 and cos theta is 30-degree climb. So if you substitute that, you will get a value as 0.01725 because they asked it 10 power minus 3, so just move the decimal back 1, 2, 3. So it is 17.25. Yes, guys. Hope you guys don't have any doubts in this, right? Very simple, isn't it? So we have to keep solving problems, unless you feel until you feel confident. Okay, right? I can see, like I said, problems like these are more to come. No, it requires basic application of your problem solving skills. Right? This is the last question of today's session. An aircraft is flying with inertial ground at wind speeds of VGB, which is 105 meter per second. These are the UV and W components. VWB is 0 minus 5 minus 10, again UVW components, respectively, as expressed in the body frame. The corresponding side slip angle is dash. Okay. So this is a pretty simple problem. So we have inertial speed and inertial speed and ground speed, wind speed. Okay. So let's determine the total speed. So how would you determine, let's say, from inertial you are measuring some speed, and from the wind you are measuring some speed. Okay. So this will be what the resultant between the two velocities, right? So it has to be something like this. It is under root of, so I have coordinates, right? 2 points. So it's 100 minus 0 to the whole square plus 5 plus 5, 5 minus 5, so it will become 5 plus 5 to the whole square plus, then I have 5 minus of minus 10, it will become 5 plus 10 to the whole square. Simplify this, you will get it around 101.612 meters per second. Okay, bracket this is the net velocity. If I just put it in the vector, this is the modulus of the velocity vector, right? I know that, we know that the vertical velocity is simply the modulus of the velocity vector times the sine beta. Okay, so which means what? So what is the vertical velocity? It is basically 5 minus of minus 5. So this will become 5 plus 5. That is basically 101.612 times sine beta. So from here get beta. So beta is sine inverse of 10 by 101.61, and it turns out to be 5.647 degree. So bracket this as well. So this is your answer. Hope you guys don't have any doubts in this, and you can just fill it in the blanks as option B. Okay. Right, guys? Pretty simple, isn't it? Like I said, no problems. Very simple. Very simple in Git. If you have solved more problems by taking a test series, then this would be pretty easy for you, right? Okay, guys. So with this, we wrap up today's discussion on Gate and Gate previous year Gate questions. And I hope you have enjoyed this session. And please, stick to solving more and more PVQs because, like I said, your Gate exams are nearing. So please prepare well, and I wish you all the best once again. And please subscribe to our channel, and I would like to thank you all for attending this today's sessions, and please subscribe to our channel so that it motivates us to do more and more videos like this. Okay, fine, guys. If no doubts, then we'll wrap up today's session, and thank you and have a good day. Bye bye. Okay, so Swastik Panja has said, can you please repeat question number 55? Okay, fine, no issues. Right. Okay, let's take this problem. Pretty simple. Okay. Let me just try to draw it separately in here, okay, so that you see. See, so the general expression for the, okay, just write general expression for the directional static stability uh, with a vertical tail, is simply given by Cn beta equal to eta v v bar Cl alpha of the vertical tail times 1 plus d sigma by d beta. Okay. So let me explain what are those terms are. So you have the aircraft. Let's say, let me just draw big aircraft, something like this. Let's say this is the location of the vertical tail. Let's say this is the location of the center of gravity. The distance from this to the tail is basically my LV, which is the tail moment arm. Eta V is basically, it is half rho V square. The ratio of the dynamic pressures at the vertical tail to that of the whole aircraft. Okay. And VV bar is the platform area of the vertical tail times the moment arm length. Okay, moment arm length is C. Imagine if LV is increased, what will happen is if you deflect this, let's say, then it will produce more moment, right? Because if the same force exists, this force times the larger distance LV, let's write it here. Let's say the F, let me deflect this to here. F times LV, right? So if I keep the force constant, increasing LV results in increasing the moment, right? So that's what its name is, the tail momentum. Okay, that's what you have to remember in here. Okay, right. So this is basically by S into B. times this sigma is the downwash. Okay, basically, your tail is, because your tail is situated in this fashion, your wing will basically, a flow or a wing, will have an effect on this tail. Okay, because the wing basically influences the flow field, and your fuselage will also influence the flow field. So the sigma is basically a downwash component. Okay, most cases it is neglected to zero, but in real life it's not the case. Okay, right. So these are the cases in here. So I can directly see that C and beta is proportional to the LV over here. Okay, so C and beta is proportional to LV. So which means if I increase LV, this results in an increase in the C and beta. Okay, and C and beta is basically the stability component, the directional stability. Okay, so the directional stability increases, right? That's what is the case, right? Hope I have answered your queries, Swastik Panja. I hope you don't have any doubts on this, right? Please feel free to put it yes in the chat box, so that that helps me to understand whether you have understood or not. Okay. Okay. So fine, guys. So if no doubts, then we'll wrap up today's session. And please subscribe to our channel and please keep watching our videos. We have so many PVQ sessions, being organized by our reputed faculties. Please, work out all the problems and prepare well for your gate exams, right? Okay, fine. So if not else, let's wrap up today's session and see you. Have a good day. Bye bye.